So in my presentation, I will give you a short introduction and some basic concept of MPM, but don't worry, I won't kill you with the equation. And then I will go straight to the application about anchor pull-out, slope stability, and tunnel gashing. So as we all know, large deformation problems are pretty popular in geomechanics. Think about pile installation, slope stability, problem of erosion or liquefaction, underground excavation. And the simulation of large deformation problem with the standard updated Lagrangian FEM is not easy because you have trouble with element deformation. In order to overcome this difficulty, several continuum-based methods were being developed through the years. For example, the arbitrary Lagrangian-Eulerian method, coupled Eulerian Lagrangian, SPH, particle finite element method, and the material point method. Some of them are also available in commercial software, such as Abacus, for example. But today we will talk about the material point method. The MPM uses two levels of discretization. On one side, the body, soil, is discretized with a cloud of material points, and this material point traces all the properties of the continuum: mass, velocity, stresses, strain, material parameters, and so on. On the other hand, we have a background finite element mesh that covers the entire space where the body is expected to move. This mesh is used to assemble and solve the governing equation of motion, but does not store any permanent information like in the finite element method. So at the beginning of each time increment, the information is mapped from the material point to the node of the grid. And at the node of the grid, we solve the governing equation of motion, like in FEM, very similar. And then we use this solution to update all the quantities at the material point level: strain, stresses, state parameters, velocity, and position of the material point. So the material point will move through the mesh. So large deformations are simulated by material point moving through the mesh. This method has several attractive features. For example, while it is well suited for large displacement problems, it is very similar to FEM, which is good because it means that people that are already familiar with FEM can easily start using MPM with little effort, but also that all the mathematical development that we had through the years, through the decades about FEM can be transferred to MPM. Then it applies a Lagrangian formulation, which is good for history-dependent material like soil. And it is easily parallelizable, which is good for computational efficiency. The method was originally proposed by the group of Professor Deborah Sulsky in the 90s. The first formulation was one-phase, dynamic, explicit, and these were the first blocks to build this framework. But through the years, it developed with a lot of improvement of the stability and accuracy of the method. Several multi-phase formulations were developed, which is very important for geomechanics because we have a lot of problem of soil-water interaction. And also some other features like contact formulation for interacting bodies or advanced boundary condition for seismic or rainfall and so on. And now there are a lot of development also to couple MPM with other methods, FEM, DN, CFD, in order to exploit the best functionalities of all the methods. Examples of application are, for example, granular flows, also impacting structures, slope stability. This is nice because we can simulate the progressive failure of landslide, co-seismic landslide, dam and levee failure. And I think this is a very promising field because in this chart I put the number of real cases. So real landslide, not model slope or experimental cases that are fundamental for the validation of the method. But in this chart, I just put the number of real landslides simulated with the material point method in research papers through the years. And as you can see, there is a very sharp increase of the number of real cases in the last few years. This means that the method is probably now mature to be applied to real cases. And on the left, you can see an example of a real landslide. This is the Oso landslide simulated with the MPM. Usually, these cases of real landslide are cases of rapid landslide. There are no example of slow landslide. This is because most of the formulation are dynamic and explicit, so it will take you a lot of time to simulate very long processes in slow-moving landslides. Then other applications are soil penetration problem, shallow foundation, anchor pull-out, pile installation, or CPTU, or other installation problems. Then you can also simulate erosion, because there are these coupled formulation with multi-phase, suffusion, tunnel gashing, and so on. There are a lot of available MPM software, freely available online. This is a short list of those ones that are that has been also used for geomechanical application. Some of them are very basic MATLAB or Python implementation, which are very good especially for students that want to learn how to how the method works. I mean, the numerical features. Others are more advanced Fortran or C++ implementation with a lot of features, and they are also very computationally efficient, and you can really do amazing simulations with them. The code that I'm using, and of which I will show you some example now, it's Anura 3D, which is open source, and it was initially developed in the framework of FPT7, of a European project, and it is now developed by the community of this university and research center that you can see here. Since I don't have much time, maybe I'll skip this and I will come back later if I have time. So I will show you an application of rainfall-induced slope collapse. This is a very, I would say, relatively simple application, and I use this one because I want to show you why I believe that the method could maybe in the future help us to advance the state of practice. So in this physical experiment, there is a slope 3.5 meters high. There is a layer of base clay with an inclination of 32 degrees, and above it there are 60 centimeters of loose sand. And we applied a rainfall intensity at the surface of the slope, and we measure at these black points, these are tensiometers and hygrometers, the evolution of water content and suction. So when the wetting front start moving from the surface to the top, we have a first increase in pressure and water content. Then when the wetting front reaches the impermeable boundary, it starts moving to the top, so the slope is saturating from the bottom, and after more or less 1.5 hours, the slope will fail. So the standard practice of analyzing this kind of problem, this physical test, is to first calculate the pressure distribution with the seepage analysis, let's say with the I don't know, Plaxis, FLAC, or here, for example, we use the GeoStudio, SIPW. Then you use your stress distribution and pressure distribution to calculate the factor of safety, maybe with the strength reduction method with FEM or with the limit equilibrium method with GeoStudio. And then you know that when the factor of safety is more or less 1, you are at the limit equilibrium and the slope will fail. And this is standard practice. I think that most of the people in this room are certainly able to run this calculation. What you don't know is what happens after failure. We developed a procedure to map the results at failure of FEM to initialize the quantity at the material point level in MPM for Anura 3D, and then simulate with Anura 3D only the large displacement, so the post-failure behavior. So these are the results of the CPAG analysis. We, of course, accounted for the unsaturated behavior of soil. You see the evolution of pore pressure with time. Then, with the global limit equilibrium method, we calculated the factor of safety at different times. And we say that when factor of safety is equal to 1, this is our time of failure. We take the result of FEM and we transfer to MPM in order to simulate only the post-failure behavior. The MPM formulation here is fully coupled. It means that it's a two-phase simulation. We are solving at the same time the momentum and mass balance equation of solid and liquid separately, accounting for the interaction between them. And here the constitutive model was just more Coulomb, but you can use more advanced one. So this is the initial pore pressure and vertical effective stress distribution. And then with MPM, you can simulate the large displacement. Then we also compared the displacement we got numerically with the result from PIV, from the image analysis of the experiment, finding relatively good agreement. So we can say that traditional methods like FEM, LEM can be used in conjunction together with MPM in order to optimize the computational cost, because running this CPAG analysis with FEM is super fast and easy. And I believe that MPM can help to estimate the post-collapse displacement of the slope, and maybe it could be something that can help us to move beyond the concept of factor of safety. Here I put, sorry for the Italian, but it's only a small piece of the Italian norm, saying that for, maybe it's the same in other countries, but basically here it is saying that for natural slope, the level of safety, margin of safety, basically the factor of safety, acceptable, decided by the designer, must be decided taking into account uncertainties, level of knowledge, and so on, many different things, including the consequences of the landslide. So the consequences of landslide is something very difficult to estimate with the tool we have now. Probably we can only use experience for that, but maybe having a tool that can tell you something about that could be useful, support for this kind of decision. The second application is an application on tunnel gashing. So I saw many presentations on tunneling, and I know you are expert on that. I am not. But what I know is that this problem is when you have a small opening in the tunnel lining, and water and soil start entering the tunnel, and this might creates a change in the stress level around the shield, and the phenomenon will, exaltate up to the collapse, and these are some cases. So we tried to simulate that with the material point method. So we took this tunnel lining with a small opening at the top in this case. It is a 2D plane strain analysis, although the problem is usually three-dimensional, but to start, we did this simplification. The material is saturated, and the formulation is fully coupled. So we are considering the change in pore water pressure and effective stress coupled. We also have frictional contact between the tunnel and the soil, and we assume that the soil that enters the tunnel will leave that area. So what we were able to estimate is the evolution of the displacement field around the tunnel with time. And we could identify what we call a flow zone, which is basically inside the shear bands, and with a large displacement, then a disturbed zone and a stationary zone. Then we could calculate the pressures, earth pressure and water pressure around the tunnel with time. So clearly, earth pressure and water pressure goes almost to zero at the opening, but then it redistributes around the tunnel. This information can then be mapped to an FEM model, for example, to evaluate the deformation of the tunnel. In this simulation, our tunnel was rigid, but in the future we will consider also deformable tunnels. We then explored different locations of the gashing. So from the angle 0 at the top to 180 at the bottom, and this clearly affects the rate of soil gashing, but also the contour of displacement that is completely different in these three cases, and also the distribution of earth pressures. So these are information that could be useful for evaluating the stresses and the deformation of the tunnel itself. I don't know how much time I have. Yes, so I can go back to the case that I left behind. So very short. This is an application for an industrial case. At that time, there was this, this company, Sea River, that was developing a passive anchorage system for the stabilization, where to slow down the movement of slow-moving landslide. They use basically these anchors, grouted bar with a certain plate, in order to slow down the movement of the landslide. At that time, they had a lot of questions, like, what is the best shape of the head of this anchorage? What is the optimal installation distances? And so on. So we did some work together. For example, one of the examples is that we simulated, we performed some laboratory experiment in a sandbox, 1 meter and 80. The anchor is placed at the center, and it is pulled with a constant velocity while measuring the pull-out force. And we tested different shapes, the thin square, which is the standard, I would say, square, then short, medium, and long frustocone. And then there is also another set of experimenting with the plate, half of the plate placed at the lateral boundary in order to evaluate the displacement of the soil. And here is a picture. This is grayscale. So the lighted area are the area of soil that actually displaced together with the movement of the plate, and we calculated the ultimate resistance. Then we performed some numerical tests. These tests are three-dimensional, so we draw the correct geometry of the anchor, and we applied the contact at the interface between soil and the anchor. We applied the prescribed velocity at this anchor, measuring the resistance at the anchor itself. This experiment was on dry sand, so we didn't have coupling with water. And we were able to get a relatively good agreement between the ultimate capacity of the anchor from the numerical model and the experiment. And with the numerical model, you can explore a little bit more about the evolution of displacement around the anchor. Here we have large displacement. So it wouldn't be possible to do this simulation with FEM. We tried at the beginning, but for this application, we really need to reach large displacement, so it wasn't working. Then you can do a lot of other parametric analysis for the optimization of the system. For example, consider different spacing, You can study the effect of friction angle or other soil parameters and so on. So this is a case of industrial application for an optimization of this kind of feature. Okay, so I can move to the conclusion, and I can say that, MPM is a discretization method. It is well suited for large deformation problem. It is based on the continuum mechanics and has several similarities with FEM, which is good for us. And nowadays it has been applied in many geomechanical problems. At the moment, it is still mainly used for research projects, but I believe it has the potentiality of advancing the state of the art and also the state of practice in geotechnical engineering. With this, I finish my talk, and I thank you for your attention.
Thank you very much for the nice presentation, very interesting. Are there any questions? We are not in due time, but we have the time for the questions, by sure. It is not your fault, it was our fault, the delay. No?
I kept 20 minutes.
Thank you, Francesca, for the excellent presentation. I would like to ask you, you said in the problem with the tunnel that you do your analysis and then you have to go to finite elements. But what is the reason? You cannot do everything with, let's say, MPM?
The reason, I mean, we solved it, we will solve it in the future because it's not very easy numerically. But the problem is that nowadays, in this code, in order to have a good, an accurate estimation of the pressure around the tunnel, we need that this boundary doesn't move, or at least doesn't move too much. So since we wanted to calculate the reaction accurately, we had to keep the tunnel fixed. If we make it moving, we will lose accuracy in the forces, but we get the displacement. So it's a matter of deciding what you want to get. And then there is another issue, I mean, how to model the joints numerically with this code. I mean, you have to apply, some stiffness in, rotation and so on, which are features that we don't have yet, but I don't think they are very difficult to implement. So.
And the tunnel, could it have a stiffness or it has to be rigid?
No, in that case, it could have a stiffness. Actually, now we can do a linear elastic material for the tunnel or even more Coulomb. In that case, we will get the displacement of the tunnel, but probably we will lose accuracy on the stress, on the reaction forces. So it's.
Thank you.
Are there any questions, Alexandru? Please wait for the microphone.
Thank you very much for the presentation. Maybe a short question related to the discretization, because it's a discretization method. Is there any general rule, or how do you choose the size of your discretization?
Yes, good question. Actually, for the so you have two levels of discretization. One is the size of the mesh, the elements, and the other one is the number of material points. The size of the mesh has the same effect of FEM. So the mesh that you would use for your FEM problem, it's good also for MPM. Remember that but here I didn't say, but we have linear element. It means that it should be a little bit smaller in general, but it's comparable. Regarding the number of material points, you can decide the number of material points per element. So this depends on how much displacement you have. One thing that you should avoid for sure is having empty element. Empty element means that you have just a few material points that are moving long distances, so you will create a lot of empty space in between, and this is not good. So number of points depends on how much it will move, basically.
Mm-hmm. So, one question more.
Thank you very much for your presentation. According to your experience, what is the confidence you can have in the internal forces you are computing with MPM, like, for example, in piers or in retaining walls? compared, for example, to a finite elements method?
Good. This is also a good question. Finite element is more accurate, for sure. Then it depends. The reason is because FEM use Gauss integration. Here we use material point integration, which is similar but not optimal. So okay, there are a lot of work on the accuracy. Okay, but it also depends on the displacement you have. If, for example, for a pile, if the soil around is not moving much away from the pile, it's pretty accurate, I would say. If you have something like an impact of granular flow on a wall which is deforming and so on with a lot of large displacement, then if you have many, we call it grid crossing, so when the particle moves from one element to the other, you lose accuracy. There are methods to improve it, but still is not at the level of FEM, that's for sure.
So, thank you very much.
Thank you.